Okay, so we begin our study of current electricity, meaning electricity that's moving. The last thing we studied was electrostatics, meaning it wasn't moving. So electric potential is more commonly known as voltage. You've probably heard and maybe used that term before. Voltage is defined as work per charge, which is the same thing as, or can be thought of the same thing as energy per charge. And when we think about voltage, this is what we should think of as energy per charge. So we have a situation over here where we have a bunch of positive charges on a plate, so a piece of metal, and then a bunch of negative charges on some piece of metal. This is called a capacitor, so I think we're going to have time to build one of these in class. And if a positive charge were just stuck here, it's obviously repelled from here and attracted to here, so it would go in this direction. So we can say that between these two plates of the capacitor there would be some electric field. You don't actually see red lines in space, but there's a property of space, and that is that if you put a positive charge here, it would go in this direction. This is very similar to Earth, and if we have a mass up here, you know that if we just sort of let it go, it's going to fall. So we can actually draw lines pointing towards Earth and call that the gravitational field. We don't actually see blue lines out in the sky, but there is a gravitational field, which means that a mass placed in that field is going to experience some force, same with the electric field. So as this positive charge moves through this distance, it has lost or moved through some voltage or some potential. So these two words, potential, which is short for electric potential, and voltage are sort of used interchangeably. So the positive charge would have moved through some potential or through some voltage. Just like the mass falling down lost some potential energy as it moved towards Earth. Okay, lots of sources of voltage. Get out of there. So this hopefully looks like the wall socket, and here in America we got 120 volts, so that's a lot. Don't go sticking wires in there or something. This is a little AA battery, probably familiar with these, which is 1.5 volts. And a car battery, so not drawn to scale. There's a car, there's a battery. But car batteries are 12 volts. And then the car battery is designed to start the motor, so it's designed to produce a bunch of current very quickly. So here we are, hopefully this works. Okay, so here's a little schematic of a car battery. It's basically lead. We have two different types of metals, and on the next slide we're going to talk about batteries. But it looks like this, where you have different plates and then some acid, so dilute. What would this be? Sulfuric acid. So yeah, don't go pulling those apart and spilling it on yourself or something like that. Okay. Formulae. I like the way this word sounds. Makes me sound all British and intelligent. The formulae. So we have that current is equal to change in voltage per resistance. And this is called Ohm's law. Ohm's law. And sometimes this is written as V equals IR. So you'll see it written both ways, like this and like this. And the units for, so these are the same formula, but they're for finding the voltage of something. So it's defined as the current times the resistance, and the units for voltage are volts, V. And a volt, because it's energy per charge, could be defined as a joule per coulomb. So that got a little messy there, but know that a volt is a joule per coulomb, and those are the units we use for voltage, V. It's nice, and we wish that slope were S and all that stuff, so it kind of works out conveniently. Okay, current. So current is defined as the flow of electrons. It's not really it definitely isn't the, however I spelled that, electrons. The positive charges don't move, but the electrons are pretty free to move. So we talk about charge per time, So how much, imagine you are watching this wire and electrons are flowing through it like that, and you're counting them. How many have passed per time? That is what we talk about when we say current. So a formula for current, we can say that the current, yeah, no, there it is, the variable I. We use I for current, and it is the delta Q per delta T. So amount of charge per time. The units are amps. So an amp, and an amp would be a coulomb per second. Amp is short for ampere. And I have here just diagrams of 4 different wires. And so the question is, if these wires were made out of the same thing, so the same metal, different metals have different resistances, or resistivities, but if these were all made out of the same metal, which would have the highest resistance and which would have the lowest resistance? So hopefully you're thinking about that. The reality is that, well, let's talk about current. So the most current would flow through this. The most through there, and then the second most through here, and then third most, and then the least current would be this. So the least current would flow through this type of wire, and because it has the highest resistance. Notice these are fat, or they have a greater cross-sectional area, right? These are long, these are short. So those two things play a role. What could we say? So imagine, think about this. Imagine there's a hallway. Bunch of students in the gym, and they're all trying to get out through some hallway. Right? This would be the easiest for them to get through, because once they're through, they just sort of run off in all directions. There's a fire in the gym or something catastrophic. And this, it's a wide hallway, but they have to kind of bunch up. And then, when we get to a hallway like this, students are having to run single file, and it's a long hallway. So it'd be most difficult to get out through there. So we can say, I'll just generalize here, and say the length of a wire slows down current. I'm going to write that. I'm worried that students only write what I write. Length of a wire slows down current, and width of a wire speeds up current. Or resists less. So it's not the same thing as speeding up. Okay, next page. Oh, that's messy. So let's take a look at these diagrams. So this is a cartoon representing Ohm's law. So for Ohm's law, we had V equals IR, or it could be written the other way. So Ohm's law. So this is describing the relationship between ohm here is the resistance when we talk about current flowing through a wire, and amp here, this poor guy, and this is the current trying to pass through the wire, and then volt here with these big strong muscles is the voltage trying to push the current through. So we're going to talk about circuits here soon. And basically the voltage is what forces the current through the wire. This would be the wire. And then amp, or the electrons, or the actual current flowing through, and then the ohm, or the resistance, actually slows down the current. So I thought that was cute. Also, hopefully helpful with conceptual understanding. So let's get you out of there. Alright, so here, these are just different variations of Ohm's law. If you like formulas, you could write those all down. It's the same formula, just rearranged. That's cool, Ohm's law. And then, I was saying in America, we have 120 volts in our wall plugs, and if you've traveled to Europe or South America or whatever, you probably had to get some conversion things. So this is interesting. All the blue countries, dark blue, they're using 220 volts at 50 hertz. So this is the frequency with which it oscillates. We have AC current in a wall socket. That's different from DC, alternating current, and then direct current. So AC current is from wall sockets, and that's why these have a hertz associated with them, a frequency. And then, so here we are, 100 to 127, so 120 volts. All these countries, and then, that's a little weird. Oh, just 50 hertz, and then 60 hertz. Okay, cool. So know that if you're traveling. And then here's a zoomed in diagram of a wire and what's actually happening. So we have metal atoms, and the electrons in metallic bonds are pretty free to move, which is why metals make good conductors. So these blue things are the electrons, and we can think of this as a wire, and they're just kind of free to move, and they move along and move along. But they're obviously going to experience some resistance just with the attraction to the nucleus and also bumping into other things. So there's a whole branch of technology that looks for superconductors. If we had superconductors, a lot of technology would be possible to us, and we could also transport energy over long distances without it diminishing, and would sort of help our energy crisis. Okay, so the battery. Very basic battery looks like this. So this guy, Alessandro Volta, I think was his name, he created the first battery. So here's an image of, I think, one of the ones that he actually created. These are just plates, and I think he used copper and silver, plates of different metals sort of stacked one on top of the other. These would be the electrodes or the terminals of the battery. And he had to put some kind of an electrolyte between the two. So I think it was flannel and brine, so like salt water. And in class, we'll get to do something like this, where we use pennies and zinc washers and put cardboard in between them, soaked in salt water, and from that we actually get a voltage across these terminals. So we create a battery, and it's kind of cool to see it actually work. You can connect batteries together. So these batteries are connected in series, we say. Not like the Apple woman. Ha ha ha. Okay, so if these were a couple AA batteries, 1.5 volts and 1.5 volts and 1.5 volts, yeah, you guessed it, combined like this, they would create a voltage of 4.5 volts. So later, soon, we will talk about series versus parallel, but for now that's all good. And when we're making circuit diagrams, which is, I like these, and we're learning about these very soon, so circuit diagrams, this symbol indicates a battery, and the long line is the positive terminal, and the short line is the negative terminal. Okay. So take a look at this. This is the inside of a battery. So it's kind of, you see how we have two metals that are close to one another, and these two metals have different electric potentials or different electronegativities. So one of them wants to give up an electron, and one of them wants to take an electron. So instead of just sandwiching two penny-like things, this is these different layers that are sandwiched together and then separated by some like a dielectric material, an insulator, to form a battery. Don't take AA batteries apart, because there's toxic stuff in there. Resistance, so let's define this. So this is whatever keeps current from flowing. And in the previous slide, I showed you that diagram, right? There's attraction to the nuclei plus the electrons bumping into stuff. Different metals have different resistivities. So I'll write that out. Resistivities. So when we look at this formula, this is related to those diagrams of the wires that I showed you in the previous slide. We can say the resistance of a wire is equal to rho, that's a Greek letter, times length divided by area, so cross-sectional area. And I'm going to write this in because people are frequently confused. So rho, and that is resistivity. So it turns out that most of the wire we use is copper wire because it has a low, when we talk about the cost of it, it has a low resistivity per cost. And the units for resistance are, I like the upside down horseshoe, and these are ohms. Ohms for units of resistance. And again, this resistance that we're talking about here, this is just for the resistance of a certain section of wire, right? And that this is length and this is cross-sectional area. This is the same as the resistance in the previous slides related to voltage and current. Okay, and here these are resistors, so we're going to get to use some of these, and all these lines and the color coding means something in terms of how much resistance they afford. If you were to pull apart some electronics device, there's going to be all kinds of those things wired together. What do I say? When a continuous path is connected between the terminals of a battery, have an electric circuit. So a complete circuit is one where current flows, and an open circuit is one where current doesn't flow. And here's a diagram. So we could have something like this, and like this, and like this. So this would be the battery, and this would be the resistor, for example, light bulb. So these are some of the first things that we work with. Resistor, aka light bulb. So we'll start with these real simple circuits and know that, so this is where sometimes we complain about the history of science. As this is drawn, this is the positive side of the battery and this is the negative side of the battery. So we know that the electrons actually flow that way, counterclockwise. But just by definition, we say that conventional current flows positive to negative. So this is just because the scientists who were talking about the flow of electricity didn't really understand that it was the electrons moving, so they just said, oh, well, let's say it's from the positive to the negative, and we're stuck with that now. So it's opposite what's actually happening. But that's okay, we can deal with it. I think I'd like to show you. So if you like the formulas, check this out. This is all these variations of Ohm's law. Move this guy out of the way. We haven't talked about power yet, but we will. So yeah, you might want to pause and write those down. That'd be cool. Here is an example or diagram of Alessandra Volta. So we have these piles of copper and zinc, flannel soaked in brine, and then he hooked them up to frogs' legs, and the frogs' legs twitched. People thought that was really weird, and so is electric current, making muscles twitch. And then here's our simple circuit that I just showed you on the other page, where we have a battery and we have a resistor. So the load, the resistor would be a light bulb, and the battery looks like our 1.5 volt AA. Okay, thanks for listening.